Hi, welcome to the session Net 305. Today, we will talk about Net DevOps, a modern approach to AWS networking deployments. My name is Sid. I'm a principal solutions architect with AWS. I am joined today by Akash and Michael from GE. First things first, why do we need a modern approach for networking deployments? As I thought about this myself, I concluded that it all ties back to innovation. Organizations are building modern apps. These modern apps are impacting customers and scaling at a pace never seen before. Now, computer networking is nothing but a set of technologies that enables these modern applications to communicate with each other and with its consumers. So, for these applications to scale and innovate, the underlying networking infrastructure has to scale as well. And this is why we need a new, modern, agile way of networking deployments. Now, DevOps is a combination of cultural philosophies, practices, and tools that accelerates an organization's capability to serve and deliver applications. That means faster changes, leveraging automation and rigorous testing, reducing the overall software delivery lifecycle. Now, by bringing networking into DevOps, the core principle does not change. The high velocity delivery of apps and services is still the end goal. But to meet that goal, networking infrastructure will change faster. We will make changes faster. We will do automation and rigorous testing to ensure stability. And in all of this, we are making sure that networking is not the bottleneck. Now, in today's session, we will lay the foundations of how you achieve this. And we'll also hear from GE on their journey with NetDevOps. Now, in order to formulate an implementation strategy for NetDevOps, we need to take best practices from DevOps and apply them to networking. We know DevOps approach has been highly successful and widely adopted, so why not start there? The first best practice has to do with breaking down monoliths. No, I'm not talking about breaking down the mysterious monolith that showed up in the Utah deserts. I am talking about monolithic architecture where multiple smaller components are tightly coupled with each other. So a change in one single component affects the entire architecture. Because the area of impact is big, it is very sensitive to change and requires heavy testing. This overall creates complexity and leads to slower pace of innovation. So we break the monolith into multiple smaller microservices where we manage, maintain each component individually, reducing the overall complexity and increasing the pace of innovation. Now you must be wondering, why are we talking about monoliths? Well, because networking monoliths exist. Let me give you some examples. As an enterprise, you probably have tens, if not hundreds of applications, and each app is probably hosted in multiple environments like dev, test, prod. Deploying all your applications and environments in a single VPC is a great example of a monolith networking design. Another example of a monolithic design is creating a single transit gateway route table and associating all your VPCs to it. Now, don't get me wrong, leveraging a single VPC or a single transit gateway is a great way to get started. But as you grow and deploy more and more applications, a modular architecture scales much better. To achieve modularity, a common approach is to deploy applications in different VPCs and leverage different route tables within Transit Gateway to achieve environment isolation. In the example you see in the slide, we isolate prod, dev, and shared services environments into their own separate route tables. Changes made to one particular environment, whether it's a change to a VPC or in the Transit Gateway route table, will not impact rest of the environments. Now, the exact segmentation strategy will vary based on your personal requirements or organization's requirements, but the goal is to build modular architectures like seen in this example. The next best practice is related to cultural philosophy. I want to explain this with the help of Conway's Law. I'll give you a few seconds to read it. Now, MIT and Harvard Business School actually conducted research and found strong evidence supporting this hypothesis. So if you want to deploy a modular architecture and be successful at it, you need to develop into a loosely coupled organization where teams can operate independently and with complete ownership. All this while being guided by enterprise guardrails. Here's an example of how we would apply this to the networking space. We have a multi-app, multi-VPC environment. It's the model architecture. Now, instead of a single team owning the network configuration of all the apps and VPCs, we delegate corporate complete ownership of apps, including the VPCs, to individual teams. We have App 1 and 2 VPCs owned by the application teams, the shared services VPC owned by the shared delivery team. The core networking components like Transit Gateway and Direct Connect are owned by the networking team. And the centralized inspection VPC is owned by the security team. Again, this is just an example, and an actual implementation strategy will vary based on your requirements. Now, you must be thinking, why wouldn't this create silos? How do I enforce enterprise guardrails and standards while allowing for this autonomy? Well, this brings me to the next best practice: automation. Network automation has existed for some time now, and we know about its benefits. It eliminates manual tasks, reduces chances of error, and speeds up network deployments. But in a software-defined world of AWS, automation can really unlock innovation and scale. All this while maintaining enterprise guardrails. Let's see how. Within AWS, you can define your network infrastructure as code. Using JSON or YAML, you can templatize network configuration, embedding best practices and enterprise guardrails. You can make this template available to individual app teams so they can spin up networks at scale. Having the ability to predefine a validated configuration allows for predictable and repeatable provisioning. Now, as your network configuration evolves, you can create new versions of this template and effectively track changes. AWS CloudFormation is a service that allows you to define and deploy infrastructure as code in AWS. Here's an example YAML template on your left. When deployed, creates a VPC and an internet gateway. It also attaches this internet gateway to the VPC. Now, instead of defining your infrastructure as code in JSON or YAML, you can alternatively use AWS Cloud Development Kit. AWS CDK uses the familiarity and the expressive power of programming languages like Java and Python for modeling your network infrastructure. It provides you with high-level components called constructs that pre-configure your network resources with proven defaults. Here's an example. On the left, we define public and private subnet construct. When deployed, this creates 4 subnets, 2 public and 2 private in different availability zones. Additionally, it creates 2 redundant NAT gateways and an internet gateway. Now, if required, you can override the defaults. For example, if you in this scenario, if you did not want a NAT gateway, you can explicitly state that. Now, even though infrastructure as code makes it very easy to define and deploy network infrastructure, in an enterprise, being able to deploy the changes in production environment can be time consuming. You have to go through multiple levels of testing, approvals, and this often is a manual process. So in order to accelerate this, we can leverage our next best practice, CI/CD, continuous integration, continuous deployment. The idea is very simple. You store network configuration as code in a version control system like AWS Code Commit or GitHub. When you commit a new version, a pipeline gets triggered, which automates several stages like code validation, security checks, testing, etc. It first deploys to lower environments like test and staging, and if it all goes well, it pushes the change to production. The best part, everything is automated, including fallbacks in case of any errors. Let's talk about one of the most important steps of this pipeline, network testing. Broadly speaking, there are 2 kinds of testing. You have unit tests and integration tests. Let's start talking about unit tests. Here you verify whether a piece of code base, the so-called unit, behaves as the developer intended. You can inspect the code to see if it's secure, matches intent, and follows enterprise guardrails. If you author your code in CloudFormation or Cloud Development Kit, you can leverage multiple open source frameworks that let you build these validation tests. CloudFormation Lint does linting. CloudFormation Guard allows you to define custom policies and validate your templates against these policies. And finally, CFN NAG looks for patterns in CloudFormation templates that may indicate insecure infrastructure. I have links for all of these in the slide here, so go check them out. Now, here are some examples of validation checks you can perform on your network infrastructure. If you're deploying firewall rules, you can check for overly permissive rules like allowing public SSH access. For new VPC deployments, you can ensure VPC flow logs are enabled and internet access via public subnets is disabled by default. Additionally, you can check to ensure app owners are not provisioning really large VPCs that result in wasted IP space or even overlapping CIDR ranges. Finally, if you're creating peering connections, you want to ensure that it doesn't violate your security posture. For example, you might not want a prod and a non-prod environment being peered together. Now, note that all of this validation is done even before any network configuration is deployed. That's a great advantage of using infrastructure as code in a software-defined environment like AWS. Now, once code validation is completed, you deploy the network changes in a test or a staging environment. And now you run integration tests. Here you ensure that the changes you made works as intended with rest of the network. This can be done with simple ping tests or by using machine learning intent-based verification. Additionally, you can perform load and performance tests at this stage. Let's look at some examples to understand how CI/CD testing and deployment works for networking scenarios. In the first example, we are looking at a scenario where you have an existing IPsec VPN connectivity to your VPCs, and you're looking to cut over to the setup on the right, leveraging AWS Direct Connect and AWS Transit Gateway. Now let's look at the various deployment steps and how would you approach testing in each scenario. First, we start by configuring the transit gateway for the dev VPC cutover. First step is to create a dev route table. Next, we attach the dev VPC to transit gateway and associate the attachment with the previously created route table. Finally, we configure routes. This can be static or dynamic via propagation. Now remember that these steps will be automated in a CloudFormation template. So think about what code validation would you want to perform. An example would be to verify that you attach the VPC to transit gateway using multiple subnets in multiple availability zones for high availability. Another validation would be to ensure environment isolation. That is, you aren't accidentally adding routes to the dev route table that enable access to prod environments. Once all code validation is done, you need to verify configuration matches intent. For this, we can leverage Transit Gateway Route Analyzer. Route Analyzer, part of Transit Gateway Network Manager, allows you to verify that Transit Gateway route table configuration will work as expected, even before you start sending traffic. In our scenario, for example, we can check if the source IP from dev VPC attachment can communicate with the destination IP over Direct Connect. Now, while this is a very simple scenario, Route Analyzer can be used for more complex analysis involving multiple peered transit gateways and also middle box appliances. You can see an example here in the screenshot. In order to learn more about this scenario and how you can use Transit Gateway Route Analyzer, you can scan this QR code or check out this link. As next step, we configure the VPC route table to allow traffic flow to the transit gateway from within the VPC. Now, to validate the success of this change, we can use VPC Reachability Analyzer. VPC Reachability Analyzer is a configuration analysis tool that enables you to perform connectivity testing between a source and a destination in your VPC. Now note that this does not evaluate transit gateway route tables, but rather only the VPC route tables and the gateways attached to it, like the internet gateway or the virtual private gateway. To get started, you define a source and a destination you want to test connectivity between, and optionally an intermediate component like the NAT gateway or a peering connection. In our scenario, we can test connectivity between a test instance within the VPC and the transit gateway. If you want to learn more about VPC Reachability Analyzer, here are two reference blogs which I recommend reading. These explain how VPC Reachability Analyzer can be used as a core component of your network testing setup. You can scan the QR code or check out the links. Finally, we initiate the cutover. For this, we shut the VPN connection down and run a ping test to validate success. If the ping is successful, we can proceed by repeating these steps for prod VPC. Otherwise, we can fail back in case there was an error. We can break down the entire network deployment example into 3 stages, each with its own mini pipeline. As part of each step, we deploy the change, validate the code, run tests, and if successful, move to the next step. When all these steps are successful, we move to the next phase, which is repeating these steps for production VPC cutover. The next example is a simpler one where we create a new VPC and add it to an existing transit gateway environment. We are assuming that the transit gateway already exists in the central networking account and was shared with the Spoke VPC app accounts when those accounts were created. When an app team needs to provision the new VPC, they use a self-service portal to request one. They enter their unique requirements, which gets blended into an enterprise-approved CloudFormation template. A pipeline to deploy this customized template gets triggered. The VPC, along with all the subnets, route tables, gets provisioned, and an attachment request is sent from the Spoke VPC account to the transit gateway. This attachment request triggers the transit gateway configuration pipeline. The transit gateway configuration pipeline can run automatically, or you can add a manual approval step, which requires a human to verify the connectivity request before the pipeline can be executed. Once approved, the pipeline accepts the attachment request, associates it with the route table, and configures routing. For testing, you can leverage Transit Gateway Route Analyzer as discussed before. Finally, you can configure VPC route table and run VPC Reachability Analyzer to or ping tests to validate connectivity. This can be handled as a separate pipeline or part of the same pipeline. Again, this is all very flexible and depends on your requirements. Here's a blog which covers in depth the various steps required for automating VPC attachments to Transit Gateway. Perfect. Let's recap what we have learned so far. 1. To achieve true scale, you need to deploy modular decoupled network architectures. 2. You need to promote complete ownership and evolve into a loosely coupled organization. Here we saw examples of how you can isolate VPCs, modular VPC infrastructure, and provide ownership to individual app owners. Next, we saw network deployment should be automated with infrastructure as code. We saw how CloudFormation works. We saw how Cloud Development Kit works. And finally, we saw how you should be using CI/CD pipelines that integrate network testing along with code validation, security checks, enterprise guardrails for every networking deployment. Providing autonomy to individual app owners and individual account owners does not mean that you're getting rid of your enterprise guardrails. Using infrastructure as code and overall automation, you can enforce speed, scale, along with enterprise guardrails. Now, before I hand it over to Michael and Akash from GE, I want to highlight 2 network automation solutions that you can leverage as you begin your NetDevOps journey. STNO, Serverless Transit Network Orchestrator, lets you easily set up and manage a multi-VPC, multi-account transit gateway deployment. Additionally, it provides you with a web interface that you can leverage to approve and audit network changes. It's very easy to get started. The solution comes with a CloudFormation template, so you don't have to learn infrastructure as code or go ahead and take developer classes. You can get started, deploy this CloudFormation template, the entire solution gets deployed. And if you want to make tweaks to it, this is completely open source and you can do so. The next one is an automation that allows you to inspect hundreds or thousands of VPCs and accounts in one place. For this, we use AWS Network Firewall. AWS Network Firewall is a fully managed firewall which you can use for IPS, IDS, URL filtering, and other deep inspection use cases. This solution leverages CI/CD to perform firewall rule validation along with auditing and tracking of changes. Again, this is a fully automated solution, so you will get a CloudFormation template which you can deploy and get started. You can scan the QR code or check out the link for more details. Awesome. Now I'll hand it over to Akash and Michael from GE to talk about General Electric's journey with NetDevOps and network automation.
Thank you, Sid. Hello, everyone. My name is Michael Palmer. I'm a staff software engineer on the cloud hosting team at General Electric. And today I'm joined by Akash Varga, who's a principal infrastructure architect on our networking team. Today we want to discuss some background on General Electric, talk about some of the benefits that we've experienced with automation, and we're going to explore a couple of use cases for automation today and automation tomorrow. We're also going to briefly touch on our migration to Transit Gateway. So who is General Electric? We're a global company in over 170 countries. We're actually more like a company of companies. We've got a bunch of business units. Some of these you may know, such as aviation, healthcare, renewable energy, and power. We have about 174,000 employees, and we partnered early on with AWS with a challenge to move 50 apps in 60 days back in November 2013. Today, we utilize almost every AWS service out there. So who is the cloud hosting team? Cloud hosting is actually horizontal. We're comprised of 50 DevOps engineers with multi-platform, professional level cloud certifications, and we have a single UX brand manager. We work closely with several teams, including network engineering and operations, DNS engineering and operations, cyber, compliance and threat intelligence, identity, and those G business units I mentioned, who are actually our customer base. So what do? We perform VPC builds and decommissions through a product line we call Guardrails, which allow VPCs to be connected or disconnected to or from our network and provide bundled security controls to protect the company. Our team also oversees cloud billing, cloud education, cloud networking, and cloud identity. And we build tools and microservices to protect and govern GE and make all of our lives easier. And where we can, we automate, automate, automate. So we have a philosophy of customer independence. We want to enable our customers to be able to do their work, but we want to be able to add our guardrails in to protect the company. We accelerate innovation, and we stay on the bleeding edge. We love to test new services when they are released, and we perform tons of POCs. We push boundaries. Change is not always a bad thing. We have a cloud-first, cloud-native mentality. Whenever we can, we push for a service to be built in a cloud-native service. Our mentality is, if there's a service for it, then we should not be running an instance for it. And like I said before, automation. Automation is layered within the fabric of our services, and it makes all of our lives easier. One of the systems that uses this automation is our ordering platform, which is how internal teams, or those business units I mentioned, order connected or disconnected VPCs. It'll go through an approval workflow before our team receives the order, and then we will use our automation to build the AWS and networking resources. We'll also perform quality assurance checks before we release the account back to the customer, and later on, if they have no longer a need for the account, they will decommission it back to us. So I'm going to hand it over to Akash right now to illustrate our global network and explain how we got started in automation.
Thanks, Michael. Hello, everyone. I'm going to give you a quick rundown about our global GE network, how we connect with different cloud providers. and where we started basically our first set of automation in terms of cloud and cloud networking. As you can see on the screen, we have redundant data centers in all the 3 poles. In the US, it's on the East and West Coast. In Europe, it's in Central and East, and in Asia Pacific too. These locations we call the POP locations. Their main purpose is 3 things really: aggregating all the branch offices, aggregating all the data center connectivity and internet exit, and basically the third thing is to connect to the various cloud providers. Today's architecture, cloud connectivity architecture, is relatively simple in terms of design, in terms of routing. So I'm going to go from right to left, where you can see how the enterprise network, the POP locations, are connecting to the cloud providers. So if we come from the right, basically our first entry point into this segment is a firewall, is an inspection zone. An inspection zone is really like a set of sensors, a set of IPSs, IDSs, and the firewall. After that, we have different type of devices. So these different types of devices are basically per function. So we have one for internet exit, we have one for cloud peering. On those cloud peering devices, we call them simply the cloud edge routers. That's where we have the direct connects are terminated, and that's where we have basically the layer 3 peering. And after direct connects, we have the VGWs, basically, and the VGWs are attached to the VPCs. So in today's architecture, it's relatively simple. It's a VGW model connecting with a direct connect, and basically for establishing a BGP peering with our cloud edge router. This is how we hand off the traffic to GE today. It's also important to note how VPC to VPC traffic is being handled, because Michael is going to talk about this in his next presentation. So currently, if a VPC wants to talk with the VPC, basically we steer that traffic, we pull back that traffic all the way back to the edge routers. This is how it's designed. This is how it has been working. So it's not complicated, but there are things which we're working on to avoid this. But right now, if 2 VPCs want to talk with each other, all the traffic is basically being pulled back into the cloud edge routers. Automation. So I'm going to talk about automation, how we first started it, what were our challenges, which are the areas we use it. So the reason we started to use automation is because what Michael has said, that in his beginning, we have many customers. We have built that big cloud catalog where the customers can go and can order basically cloud accounts for their own. We realized in the early stages that most of this is a repeatable work, right? On the networking side, it's really like repeating the same VLAN configurations with different values, repeating the same BGP peerings, obviously with different IPs. So we realized that, hey, can we just automate this? Can we remove the human error from it, and basically just create a playbook, create some automation script for these repeatable works? So in the beginning, there was a bit pushback, right? People were a bit hesitant to learn it. People were not really accepting it. But as we did more knowledge sharing sessions, we did a lot of POCs and tests. It turned out to be working, and it basically simplified from a 6 to 1 week delivery time for these cloud accounts. There are some tools we use from the different vendors. Mostly these tools are basically native tools from AWS, some different programming languages we use, and also we use devices basically from different vendors for our cloud connections. There is a playbook that we call the CloudNet playbook. So there are 4 or 5 different purposes of this CloudNet playbook. What does it do? So we mainly use this playbook to basically hook up a new account to GE, or actually remove an account or remove a peering from GE. So the main purpose of this playbook is basically to establish the layer 3 peering, the layer 3 adjacency with GE, with those cloud routers. It basically goes in, configures the devices based on a set of standard values. It creates the BGP configurations. It creates the sub-interfaces, the VLANs. It also opens up pinholes on the firewalls. So when we deliver an account or when we deliver a VPC, there are a set of predefined firewall rules in the firewalls that we have to open. So all those rules are like basically well-known standard ports like 8443. So it also goes into the firewalls throughout the network and updates all the firewalls. It has an IPAM feature too, or an IPAM role. Basically, it does a reservation to our central IPAM tool, basically making sure that no one else can basically reserve that subnet. And basically, the fourth or the fifth thing is it makes an API call to a colocation provider. So that's basically the layer one connectivity. That's basically establishing the connection, the underlay connection. Here are a couple of things, how we broken this down. So first, it does a validation check. First, it basically scans the global route table. If that CIDR block that the account has got assigned is free, is not used. This is important because if we do have an overlapping IP space here, the playbook is going to terminate immediately. It also does a VLAN validation, making sure that the same VLAN with the same VLAN ID cannot exist on the same devices. It performs a couple of device health checks, making sure that the devices that we are carrying out these configurations live is responding. There is no memory leak or there is no high-intense CPU running on these devices, CPU utilization. It also captures the route tables. So we are doing basically a route table capture after and prior to making sure that nothing drastically has changed. For example, if we did any misconfiguration, we want to see those, right? We want to see if any of the routes are missing or there is a big volume of routes which were missing after the deployment. We want to basically check those. And also there is some config snapshots. We are capturing basically the configs prior and after the change. When it goes to the deployment, right, it does the deployment on the router and switches. It's establishing the BGP peering. It establishes the layer 3 peerency, and it's also establishing the VLAN stitching, the layer 2 part as well. As I said previously, there's a firewall section. In the firewall section, it deploys those standard rule sets, what the customer is expecting to get his account delivered with. It does also an API call to our IPAM tool, making sure that that subnet can no longer be reserved for anyone else. And it basically calls our fabric provider, making sure the layer 1 connectivity is also up and running. So post the deployment, it does a post check, making sure that the devices are still reachable. It does a compare of the route table. It does a config archive, making sure we have now a newer version of the config. It also does a comparison between the old config and the right config, making sure that the only things which have changed are actually the changes that we wanted the playbook to change. So it does a comparison. And it also sends out a notification that, hey, this account has been connected to GE. I'm going to pass it over to Michael, where he's going to talk about the future connectivity of GE, cloud connectivity.
Thanks, Akos. Now I want to talk a little bit about tomorrow's network connectivity. Let's start with our migration to Transit Gateway. We see this as an opportunity to centralize our connectivity model. It greatly simplifies our peering configuration and makes life a lot easier for network engineering and operations. It keeps cloud traffic within the cloud and reduces our direct connect utilization and improves latency for VPC to VPC communications. It also enables fine-grained routing control within AWS and enables cloud-native firewalls. So let's look at this new architecture. So if you have traffic going from on-premise to AWS, we don't have all those different direct connects on a per VPC basis. Now we can go through a single direct connect. For VPC to VPC traffic, it does not have to be sent back to our edge routers anymore, just to be sent back over the direct connect to AWS to get to VPC-B. Now we can ride the Transit Gateway. So let's look at our second use case, the Transit Gateway playbook. This works with new or existing VPCs. It looks to minimize network outage on migrations and supports rollback in the event of a connectivity issue. It propagates VPC or BGP route updates to child accounts and utilizes asymmetric routing during the migration to ensure minimal downtime. We'll come back to this later. So some of the resources that are automated within this playbook are the Transit Gateway and its route tables, the Network Manager, AWS Resource Access Manager. We utilize VPC managed prefix lists and route tables, and then the Direct Connect Gateway and virtual interface. So let's walk through what this playbook does. So first off, it's going to go associate a VPC with the TGW, and then it's going to update the route tables so that that VPC can be reached. It will then advertise the VPC CIDR over the Direct Connect gateway back to our edge routers. We'll perform some QA checks, and then we're going to stop for an approval step. And we stop there because the next step is updating the VPC route tables. This is going to change the traffic going southbound to go over the Direct Connect instead of over the existing VGW. Again, we're going to do more QA checks and stop for another approval step, because the next step is triggering the DX Killer playbook. We'll come back to this later. Again, more QA checks, and then when we're satisfied with a full migration, we perform cleanup. So let's look at how the routing works with that asymmetric routing I was talking about earlier. So before the migration, we're routing the existing virtual gateway up and down on the edge router. You see the transit gateway path is there, it's configured, but it's not active. We use local preference on our routers to influence which path it will take so that we have full control of the BGP metrics for the duration of the migration. When we update that VPC route table, we change it so now we're going northbound from our edge router via the existing virtual gateway, but then from the VPC, we're going southbound over the transit gateway path. This acts as a sort of a smoke test before we shut down BGP, so we can be satisfied that the traffic can reach our edge routers with no issues. This asymmetric routing also works because we are traversing the same firewall. If we were to be going through a different firewall, we may lose, or we may get packet drops. So after migration, when that DX Killer playbook is run, it will shut down that first path on the VGW. So you see that is now inactive, which means now all AWS traffic is forced via the transit gateway path. Let's take a look at that DX Killer playbook. We built this to avoid an outage when disassociating the VGW from VPC or DX gateway. Network engineers do not need to be present for the migrations, and it supports rollback in case of connectivity issues. We actually have another playbook called DX Healer, which will perform the rollback. It puts full control of routing in our hands. It'll ensure that the TGW BGP peer is ready to accept the traffic before it will go and shut down the BGP peers of the existing interface. Through this, we were able to achieve zero downtime migrations, with the caveat that it still has to traverse the same firewall, otherwise you might get packet drops. Let's look at this playbook in more depth. So first off, we're going to look at our VRF validation. We want to see if the VRF on the existing CIDR is changing or not. Then we'll look up the VLAN for that CIDR. We're gonna verify that the VGW is properly advertising the route as well as the TGW. And once we perform all those pre-checks is when we go and we'll actually shut down the BGP peers of the VGW. And then last step is to send notifications to us so that we know that this action was taken. So let's look at some takeaways. Automation is great, but there is risk. Make sure to do lots of testing. We've done, with the playbooks I mentioned, we have done so much testing, and then we're constantly testing some more. Additionally, we make sure to log everything so that if something does go wrong, we can go and figure out what happened. And always have a manual intervention plan. All of those playbook steps are documented so that if we need to do them manually, we can. So on behalf of Sid and Akash, I want to thank everyone for attending this session. You can find us all on LinkedIn.